Good morning. This is Jerry Tuttle from the University of Phoenix, and my topic for today is those who can do, those who can't use computer simulation. And my apologies to Irish playwright George Bernard Shaw, who wrote similar lines about teaching back in 1903. Simulation, I think, is a really interesting topic. It's not discussed in a lot of math classes, but it's extremely useful to help explain concepts that otherwise are hard to explain in normal math. So some background, there are many definitions of simulation. The definition I'm going to use is simulation is imitation to reproduce behavior of a real-world system. So the key word is imitation. This is a model, and we're modeling a real-world system. And it's useful for some problems when the real world is too expensive, too dangerous, or too complicated. So as an example, this is a CPR dummy, and if you've ever learned CPR, you're pounding away at this dummy's chest, and certainly that's something you don't want to do on a live body in practice, and so the CPR dummy is an example of a simulation. Does anyone have other non-mathematical examples of simulations? Here are a few I've come up with. There are driving simulators, and in fact there are researchers, I believe University of Utah is one of them, where how do you research something like the effect of drunk driverness or driving while texting? Well, you don't want to do that with a real driver, you do that with a simulator. Any kind of disaster preparedness, fire drills. In one of my employments, I worked on the 41st floor of a building, and once a year we had a serious fire drill. We walked down all 41 floors to see what that's like, and that's a simulation of what it would have been like if we really had to do it. Various science experiments use simulation. I saw a nice one with how quickly virus spreads by pouring cups of colored water into each other's cups. Any kind of role-playing or games, management games are a simulation. But these are generally deterministic games and not stochastic games. I'm more interested in this talk for stochastic simulation. So stochastic simulation is sampling from a probability distribution to reproduce behavior of a system. And again, this can help explain and illustrate difficult concepts and can solve problems that are hard or impossible to solve directly, and simulations are often fun. Before we get into the math, stochastic simulation is used in other than math subjects. Anyone who models the macroeconomy may do that with simulation, where various variables such as inflation, interest rates, and so on, you can simulate each of these variables separately and in combination to see the effect on the macroeconomy. An example of maybe more personal example is with Social Security or other insurance and business entities, such as for yourself in retirement. You can go to a financial analyst who will simulate your financial situation. What is the chance that you will outlive your money under various scenarios of how much interest you will earn and what your expenses are? Sports nowadays are big users of simulation. Moneyball popularized this. Sports simulators can ask what happens if you take your number 6 batter and change the batting order and bat him at number 2 and simulate a season of doing that. What is the effect on the hitting for your team? And so there are a lot of uses of stochastic simulation outside of math. The simulation process is you construct a model, and this will be a probabilistic model. You design a simulation experiment. You generate random numbers from a probability distribution or more than one, and you analyze your results. There are plenty of nice online simulations that have been constructed very professionally. Here are a few I've found. Rice University has one. Rossman and Chance, two math statistics authors. UBC, I believe the BC is British Columbia. Farmington State College. So if you don't want to build your own, you can certainly use one of these others, which are very professionally built and have great graphics. But for my purposes, I want to build my own in Excel. So to do that, we're going to have to generate some uniform random numbers. A uniform random number is a random number between 0 and 1. And underneath the black box, Excel and other computer systems use modular mathematics to generate these random numbers. Historically, Excel had been criticized over insufficient randomness, and in more recent years, it's improved its randomness algorithms using Mersenne primes, which are familiar if you've studied theory of numbers. But Excel hides this from you and gives you two functions to simply create random numbers: equal rand, left paren, right paren, nothing inside the parentheses, gives you a random number uniform between 0 and 1. Equal rand between, left paren, min, comma, max, right paren, says you can input your choice of a minimum and maximum and generate a uniform integer random number. And you can easily take the first random number function and transform it to get to an interval between a and b by using the transformation b minus a times the random number plus a. If you don't want to use Excel, the Texas Instrument 84 allows you to do some random number arithmetic. You go to the math function, then PRB. Actually, the TI-84 gives you a few random functions. Rand, left paren, right paren, rand int, which gives you an integer, rand norm, which gives you a normally distributed random number, rand bin gives you a binomial distribution random number. So this is actually a little more powerful than Excel. But unless you're only generating a few random numbers, I'm not sure why you'd want to use a calculator rather than Excel. In principle, how do you generate a non-uniform random number? So if you have a probability distribution, lowercase f of x, you can always create its cumulative distribution, capital F of x, and then capital F of x, the range of capital F will be between 0 and 1 because it's a cumulative distribution function. If you're able to take the inverse of that function, and that is, so starting with as your domain numbers between 0 and 1, if you can map them back into capital F inverse, now you've created non-uniform random numbers obeying the probability distribution function of capital F. Interestingly, Excel now gives you several inverse probability distribution functions so that you don't have to reinvent the wheel. There's an equal norm.inv, there's an equal gamma.inv for the gamma function, and there's an equal lognorm.inv for the lognormal function. So some Excel Excel examples that I'm going to talk about. I'm going to talk about definite integrals, the coin flip of a run of 6 consecutive heads or tails, some famous problems, the birthday problem, the Monty Hall problem, the Buffon's needle problem, and then a few statistical applications, sampling distributions, central limit theorem, and confidence intervals. And the Excel files themselves are all available for your use at this website of mine. So first, let's start with definite integrals. You may remember when you first started studying integral calculus that not every function has a simple antiderivative. And this is one of the classic examples. The integral of e to the minus x squared over 2 does not have a simple antiderivative. And you will probably learn that fact in calculus, although most first-year calculus classes will not tell you why it is we know such a simple antiderivative does not exist. It took me a long time to find any evidence of why that is, but there is some advanced mathematics, and there's a Louisville theorem, I'm probably mispronouncing that, which does discuss why that's not the case. But if you actually needed to integrate such a function, which you do in because this is the normal probability distribution function. You can numerically integrate such functions using Riemann sums, Taylor series, and geometric approximations. But there's also a simulation solution to this, which interestingly my calculus teacher showed us in the 1960s, long before personal computers. Namely, if you can evaluate a function f of x at any particular x, you can approximate its definite integral with computer simulation. And so this is the graphical result of my having done 5,000 simulations. So here I'm simulating ordered pairs x comma y, and then I'm asking for each x comma y, is that y less than the integrand e to the minus 1/2 x squared, etc. If it's less than that integrand, then I want to count it, and I want to count the proportionate number of times this occurs, and I'm saying the proportionate number of times this occurs when related to the full area of the rectangle. That is the integral. Similar problems could approximate pi. So in this example, I've done 5,000 simulations. Here my x's are going to be between 0 and 2 because that was the limits of the integral I was interested in. Here my y's need to be between the minimum and maximum values of f, and I came up with an approximate integral value of 0.48. Here's what the Excel spreadsheet looks like. So I've generated random values of x and y. The x's are between 0 and 2, the limits of integration. The y is between 0 and 1 because it's a cumulative distribution function. And then, as I mentioned, for each simulated value of y, I ask if my value of y is less than what happens when you evaluate the integrand at x. If it is less than y, I'm going to use it. If it's not, I'm not. I do this as many times as I like. Here I did this 5,000 times, and I got 1,209 points under the curve for a simulated area of 0.48. Here's another problem. If you've used a statistics textbook by Marty Triola, This is one of his favorite problems to do. He likes to do this with a class. He assigns as a homework problem. He says, do 200 flips of an ordinary coin and count how many times you get a run of successive heads or of 6 successive heads or tails. And his contention is many people are not really going to flip the coin 200 times. They're going to say, well, how does the teacher know whether I really flipped it or not? And many people are just going to write down randomly a bunch of heads or tails. And Marty Triola's contention is I can look at your results and tell you whether you truly flipped the coin or not. And that's how often you come up with a run of heads or tails of 6. And that's because his contention is it's very frequent that in 200 flips you will get a run of 6 heads or tails, but most people don't realize this. I think that's a hard problem to do algebraically. With 200 coins, how do you algebraically come up with the probability of a run of 6 heads or tails? It's certainly a very simple problem to do stochastically in Excel. So for 200 times, I'm just going to come up with a random number between 0 and 1. If the number is less than or equal 0.5, I'm going to say it's a head. If it's greater than 0.5, I'm going to say it's a tail. And then I'm just going to count every time I get, I have six random numbers. I'm going to ask in this 6, do I have a run of 6 same heads or tails? No. In this 6, 2 to 7, do I have a run? Yes or no? No, so on. At this time I did have a run, 1, 2, 3, 4, 5, 6 heads in a row, so that's a run. So it's very easy to do this. But more interestingly than doing it once is doing it multiple times. And that's the frequency definition of probability. If you repeat an experiment under the same conditions, do the results of the repeated experiment converge to a particular solution? So I repeated this experiment, I think 5,000 times. So I did 200 random numbers, asked for simulation 1, do I have a run, and then do it again and again and again. And I'm sorry, I did this one 20 times. And in this example, 95% of the time, I did get a run. In doing this, so it's easy enough to set this up the first time, but if you want to keep track of your results, you're building a larger and larger spreadsheet, and you're creating these random numbers for the first simulation in one column, and then the second simulation in another column, and the third simulation in another column, and so on. And the spreadsheet is getting bigger and bigger and slower, and you don't want to range value your previous results, or you're not going to be able to copy the formulas. And at first I wasn't quite sure how to do this. My spreadsheets were getting bigger and bigger and running slower and slower. But I discovered Excel gives you this thing called data table. And so let's talk about this for a moment. This is a different problem than the coin simulation. Here I'm just sampling 10 numbers, and these are 10 numbers. I'm sampling from a normal distribution, I think. And I'm doing this sampling over and over again. And in this problem, I was really only interested in the mean of a sample of 10. So this cell here is just the sum of these 10 numbers divided by 10. And this is the experiment I want to simulate over and over again. So there's something called this data table function in Excel. So I built this range with a couple of headings, one one cell here. Now this cell, I'm showing you a particular formula. I'm referencing this cell B16 because this is really the formula, and this is the result of a simulation that I care about. Having done one simulation, I really don't care about these 10 numbers. I really only care about the X bar. So what I want to do is I want to do 20 simulations and really just keep track of the X bar. So this is a range I've created, and now I want to highlight this range, and the range includes the key formula here. So this is the range starting at D4 and going to E24. That's the range I want to highlight. And then data, what if, data table. Ignore the row input cell, and then it's asking for another cell just to keep track of some calculations, which I do out to the side, and then OK. And then OK will then fill this table with this many of simulations, simulating exactly this and keeping track of the sample means. So that's a very powerful function in Excel for these problems. Here's another problem. A very famous problem in probability is the birthday problem. If you have random people in a room, what is the probability two of them have the same month and day birthday? Surprisingly, 23 people is a 50-50 probability. 30 people is a 70.6 probability, and that's a probability I would bet on. There's a reasonably straightforward algebraic solution to this problem involving permutations. This is a fun problem to test in practice. If you have, say, 30 people in a room, write down their birthdays. It's kind of slow to do that, but after the 30 birthdays, you can test did they indeed have the same, two of them have the same birthday or not. But I've always found that experiment sort of unsatisfying. You know, maybe it works, maybe it doesn't. But once again, simulation, I think, provides a more satisfying solution. It's certainly easy enough to simulate 30 numbers. Here I'm using that rand between because the numbers I want to simulate are numbers between 1 and 365, where of course each of those numbers is equivalent to a birthday. So when I simulated 21, that's equivalent to January 21. When I simulate 293, that's the 293rd day of the year. That's equivalent to October 20. So I can easily enough simulate, say, 30 birthdays and ask if I have a match. So this time I did, and I matched January 17th. Here and here. I had a second match of June 18th. So I can simulate this once and see if I have a match, and then using data table, and actually the key formula is right here, which is going to reference, I don't show you, but down here, if I have a yes, I'm going to say match. If I don't have a match, I'm going to say no match. And this is in 20 simulations. How often did I have a match? It was 75% of the time. The algebraic example is 70.6% of the time, which I think is pretty close for 20. If I did this 5,000 times, I would expect my empirical result to be very close to the expected result. So that's the birthday problem. I think it's a fun problem. The Monty Hall problem. I think today's students are too young to remember guest game host show Monty Hall, but Monty Hall is known in math circles for one of the most famous math problems, only because it was discussed in Ask Marilyn in Parade magazine, and Ask Marilyn just got thousands and thousands of replies. The Monty Hall problem is Monty Hall is a game show host, and he has a contestant, and the contestant is given a choice of 3 doors, and there's something like a car randomly hidden behind one of the 3 closed doors, and goats hidden behind 2 of the remaining doors, and the contestant picks a door, and whichever door the contestant picks, Marty opens one of the other 2 doors and shows you a goat and says, well, there's a goat under one of the doors you didn't pick. Now do you want to change your choice of the door you picked? And mathematically, the optimal decision is to change your pick, not to keep it. That is a non-intuitive decision, it seems to me. It seems to me the intuitive decision is to keep your pick. Ask Marilyn on Parade Magazine patiently explained this to many professional mathematicians who disagreed with her. So there are many explanations of this you can find online, but I think this is a hard explanation to sell. But once again, this strikes me as a fine simulation problem. You can simulate this as many times as you like. You can simulate all the various possibilities. Where is the car? Which door did the contestant pick? What happens whether you switch or you don't switch? And what are the results? And the results are you get the car more times and approximately twice as many times if you switch your choice versus if you don't. It's 2/3 versus 1/3 is the mathematical solution. In my simulation, I got 77% versus 23%, but clearly in either case, the optimal decision is switch your choice of doors. Don't retain your switch. Here's another famous problem. It's Buffon's needle. I'm probably mispronouncing that. He was a French mathematician, I believe in the 1700s. And his problem is if you have lined paper, such as a lined piece of loose leaf paper, and you randomly drop a needle on it, the percent of times that the needle crosses one of the lines has a particular formula, and the formula in the long run will equal something like 2 divided by pi, and therefore this gives you an experimental way to approximate the value of pi. This problem also has an algebraic solution. It uses trigonometry and calculus. We're not going to talk about the trigonometry and calculus solution, but once again, and you could do this yourself experimentally if you like. Take a piece of paper and a needle and drop it and see what happens. But once again, this struck me as a good simulation problem. Basically, for any 2 lines, for two consecutive lines, what we're interested in is the length of the midpoint of where the needle drops. It's the distance from that midpoint to the line. And we're interested in the angle theta that needle makes with the horizontal. So these are the 2 random variables, the distance d and the angle theta. So once again, these are 2 things that are easy to simulate. Distance is a number between 0 and 1 because I've started with a no, distance is between 0 and 5. Sorry, if it was 1, I think it'd be too easy to do it. and theta is an angle. And if the distance turns out to be less than equal to 1/2 theta, then it does cross the line. When I first wrote this, having written a number of simulations, I thought it was easy enough to write this, and I was not getting simulated results anywhere close to 2/pi. And I realized what I was doing wrong is I was simulating theta in degrees, but Excel expects you to, anytime you use an angle, to use radians, and I had to change my formula to radians. But in any case, that's another fun one to do. In statistics, the central limit theorem, I think, is also not particularly intuitive to explain. If you sample from a population enough times, the central limit theorem says that your sample mean x bar should approach your population mean mu. And then the harder one, I think, to buy into is that your sample standard deviation will approach the standard deviation divided by the square root of the sample size. So this also strikes me as a perfect thing to do with simulation. I've started with a normal population. I've picked random numbers. I've transferred these random numbers into normally distributed random numbers. That's to create the population. I wanted a way to compare compare sample numbers against the population. Now I've created my random sample. I want a sample of 30. I don't show all the numbers here. So here I'm actually sampling from this normal distribution. So for example, when I choose random number 72, I'm sampling from the 72nd member of this normal distribution. So then I calculate the sample mean and the sample standard deviation. And again, I do this problem over and over again with data table. These are my empirical results that yes, my x bar is close to my mu. My S of x bar is close to sigma over square root of 30. Here are the graphical results. In particular, I think it's illustrative how small the standard deviation of the sample means has gotten compared to the population. I've also done this again with a non-normal distribution. The Pareto distribution is highly skewed, but I did the same process. I want to sample, although I've taken a bigger sample of 50 this time, from a Pareto distribution, calculated the mu's and sigmas and so on. Again, my x bar is close to my mu. Here I calculated the standard deviation of all my x bars and compared it to sigma over the square root of the sample size. Here's how this one looks graphically. This is the skewed population distribution, which goes on for quite a while. And again, it's quite compressed when I do samples. Confidence intervals are also difficult to explain. In a confidence interval, what we're asking is, if we repeat the experiment multiple times, will the confidence interval contain the unknown variable mu? And so again, this strikes me as a very good thing to do by simulation. So I'm simulating over and over again 30 sample random numbers. I'm taking normal samples from them, and I'm calculating X bar and S. So here I know what mean I'm expecting. I'm expecting a mean of 100, and I'm sampling from this distribution whose mean is 100. And then I'm asking for each time I do this, does my confidence interval of X bar minus margin of error contain mu? Here's a place where it didn't. Here my range was between 90 and 99, which did not contain mu equals 100. And sure enough, 94% of my sample times, my confidence interval did contain mu. 6% it didn't. I was expecting a 5%, but that does illustrate what I was looking for. Quickly, I'm going to talk about two actuarial problems that I've used in my actuarial career, which use simulation. Suppose I insure 50 insurance policies, where each insurance policy has an average frequency of one claim a year and an average claim size of $60,000. And let me stop right here. These are average numbers. If you're one of the people I insure, and you could have 0 claims, you could have 1 claim, 2 claims, 3 claims, you might have 10 claims. I don't think we'd renew you if you had 10 claims. So this 1 is the average. It's the expected value over a distribution of a wide range of values. And similarly with claim size, just because the claim size is $60,000, that certainly doesn't mean everyone's claim is $60,000. Most claims are small, like a fender bender. Not everyone has a full loss to a $60,000 vehicle, or a liability claim of $60,000. So this is the distribution. So two problems that have interested me as an actuary is, of all my 50 policies, if I put them together in a portfolio and ask what is everyone's claims experience for the year, what is the 95th percentile of all claims? And separately from that, how much should I pay if I want to lay off $1 million in excess of $3.5 million to another insurer? So as an insurance company, I don't need to retain all my claims business. Just as you buy insurance from me, I, as the insurance company, can buy insurance from someone else. And I can say, you know, $3.5 million is about as much as I want to pay in a year. I'd like to buy reinsurance, so if my claims are above $3.5 million, any part over and above the $3.5 million, I'm going to reinsure with someone else. So number 2 asks, what should I pay for that? So problems 1 and 2 require that we consider all possible numbers of claims and claim sizes. Anyone who's read Polya's book, How to Solve It, know that one of Polya's favorite techniques is, if you can't solve the problem in front of you, can you solve a simpler problem and use what you learn from that? So let's make this a simpler problem first and think about that, and then get back to the original problem. So suppose, to simplify this, suppose each policy can have either 0, 1, or 2 claims. Each claim is either $50,000, $60,000, or $70,000, and everything is equally likely. So it's equally likely that the probability that each of my policies will be 0, 1, or 2 claims. So each of these has a 1/3 probability, and each claim will be with 1/3 probability either $50,000, $60,000, or $70,000. So these are distributions I think I can play with and manage a little easier. So I can have 0 claims. I can have one $50,000 claim. I can have one $60,000 claim, one $70,000 claim, or I can have 2 claims. I can have two 50s, a 50 and a 60, if it's two 70s, and so on. So these I can list all these possibilities. That's called a convolution, and I can look at the aggregate distribution of all these probabilities. If I do that, I get a distribution like this. So 1/3 of the time I have no claims. 1/3 of the time I have exactly one claim of either 50, 60, or 70. And 1/3 of the time I have two claims, and this is almost bell-shaped. So I can do this in my simple case, although as the number of possibilities increases, obviously it's going to become more and more complicated to list them all. So it would be nice to have probability distribution functions that would summarize this for us. And while there are many common probability distribution functions that can be used in insurance work, and Poisson and negative binomial are commonly used for a number of claims, and these are some of the skewed probability distributions that are commonly used for claim sizes. When trying to convolute, to combine all the possibilities of numbers and claim sizes, only a few of these combinations, such as Poisson and gamma, have nice convolutions. The others don't. So now we're getting to the simulation, because if I want to use, say, negative binomial for claim sizes and log normal for negative binomial for number of claims and log normal for claim sizes, I'm not going to be able to use an easily integratable function. And now we're getting to the simulation. So it is not hard to use Excel to simulate various functions. Here is how I'd simulate a normal probability distribution function. So suppose here I want a mean of $60,000. If you recall, that's the claim size mean. And suppose my standard deviation were 40. So equal norm.iv would give me a random normal variable. Here's how I would do a log normal variable. It's log normal.inv, random number mu sigma. Here the mu and the sigma are not 60 and 40, but these are functions. A statistics book will explain where these come from. I'm not going to talk about that for the purposes of this talk. So it's not hard to do that once or as many times as you like. So I've done this 40,000 times. So for each year, I've done this with a frequency mean of 50. So this is, for example, 50 policies who've had an average of one claim. But instead of 0, 1, or 2, I've given them a negative binomial frequency distribution, mean of 50, standard deviation of 10, and a log normal distribution, mean of 60, standard deviation of 40. So each year of 40,000 years, first I simulate a claim number distribution. So maybe in year 1, I've simulated 30 claims, and then I've simulated 30 claim amounts. So I add up those 30 claim amounts, and that gives me the result for year 1. I repeat this 40,000 times. I think 40,000 is plenty for this. And now I have the results of 40,000 simulated years of experience. So having done that, as I expect, my expected claim size is 50 times 60,000, or 3 million. This is the 95% probability distribution. So 95% of the time, my claims are 4,000,001 or less. And for those claim amounts that are 3,000,005 or more, I can start accumulating how often I have amounts in excess of 3,000,005, and here's that amount. And so these give me the two solutions to my original problems via simulation. And these are two solutions I could not have gotten by direct basis, but I certainly can get by simulation. In the real world, I do not use Excel for this. Excel would just crawl if I did this. I'm using this on a company computer. I'm not sure what software they're using, but I'm sure it's specialized simulation software. And also possibly while I'm doing this 40,000 times, so is the actuary next to me, and between us and among all the other actuaries, I think we can really drive the system to a crawl, and I think actually much of this is done at night. Here are some of the references I used. So to summarize, simulation I think is a very powerful statistical technique to help illustrate some things that are hard to explain otherwise. But it's not hard to build these models in Excel, and I encourage you to do so. Thank you.